Welcome to the QA Global Best Practices Seminar. Today we will talk about what makes manufacturers the best in class in quality. In order to do that, we looked at the best ones that we have in the US market for the motor vehicle industry. J.D. Powers has created this 2017 US initial quality study that is ranking the manufacturers, the car manufacturers, according to the number of problems they had for 100 vehicles being produced. You can see that the industry average is of 97 problems per 100 vehicles being produced, and we talked with the ones who are above the industry average. We talked with them about what makes them the best in class in quality. After talking with them, we understood that there are a series of practices, a series of things that they put in place in their manufacturing process in order to be the best in class in quality. We summarized all of those into this temple, the best in class in quality temple. This comes from the Toyota Lean Manufacturing temple. It's a readaptation of that. You can see that we have some foundational steps, which would be the terminology and the prerequisites. Those would be like the basics before you can even start talking about the processes that you need to become the best in class in quality. The terminology are the series of terms that you need to understand in order to talk the quality assurance language, and the prerequisites are a series of norms to put in place in a manufacturing plant before you can start all the processes. I will go through the processes here first because I think that they're really easy to understand, especially when we talk about them from the point of view of a story, the story of the tool that we deliver into a manufacturing plant. The first thing that happens when a tool is being delivered to a plant is how can we be sure about its performance? The question is mostly relevant if we think of the different types of applications that we might be having in a manufacturing plant. We have applications which would be safety applications, critical applications, and non-critical applications. These would require different levels of performance, so there must be a way to be sure that we can easily assess what is the tool performance. That way is the CM/C&K inspection. A CM/C&K is a tool, it's a statistical tool that is capable of giving us a numeric information about the tool accuracy and the tool repeatability. Let's start with the first one, the CM. The CM is the repeatability index. It's really telling us how close, how repeatable a process is. In this case, let's think of the tool. We were talking about the tool performance. So how repeatable a tool is means how close one to the other the tightening results would be. And if we look at the drawings here, you can see that on the target, in the first case, we have all the points which are spread out one from the other. That is a case of a bad repeatability. What we want instead is that all the points will be close one to the other. So in the first case, we have a bad repeatability, or in terms of CM, we have a low CM value. In the other case, in the second case, we have a good repeatability, which means that we have a high CM value. This comes from a statistical formula that you can find there on the slide, and that is related very much to how the results are being spread out one against the other on an occurrence chart. In the chart here, we have counted the number of test results that have a specific value, and we have plotted them onto the chart. You can see if the curve, if the bell-shaped curve is a very lean one, you will have a high repeatability, and so you will have a high CM value. The CM value is only telling us how repeatable the results are one with the other, but they're not telling us anything about whether we are on target or not. That is the task of the CM/K index. The CM/K index is really looking at whether we are on target or not. In the example here, I have 3 different targets. They all show the same value of CM 2.3, but in these 3 cases we have in 2 cases, the ones on the sides we didn't hit the target at all. In the middle case we hit the target, we're right on spot. So the ones that we have on the side, the 2 examples that we have on the side, will have a low CM/K value. Instead, the target that we have in the middle of the picture, that has a high CM/K value. So the accuracy here, again, just like the CM, the higher the value, the better that is. The formula is right there, so if you can use it, you can see it if you want to understand how that is evaluated. But what I want to tell you, the important message here is the higher the CMK value, the closer the results are to the target. Let's make an example to see whether we understand the difference between the CM and the CMK value. I'll ask you some questions here. I know you can't reply to me right now, but let's take the time to think about the answer. So we have two different plants. They run the same application. The application has a dynamic torque target of 7 Newton meters and a tolerance of 0.10 Newton meters. So the minimum value that is accepted is 6.9 Newton meters, and the upper tolerance would be instead 7.1 Newton meters. Plant A has the results which are shown in the table there to the bottom of the screen, and Plant B also has the value which are instead on the right side of the table. The first question that I want to ask you is which plant has the higher CM? CM again is the repeatability. So we're talking about how close the results are one to the other. Look at plant A, look at plant B results, and think of whether plant A or plant B has the results which are closer one to the other. The answer is plant A has the higher CM value. It has the higher one because if you look at the range of the results, you will see that that's a smaller range. It's only 0.08 Newton meters as compared to 0.16 Newton meters from plant B. Now, I'm asking you the question about the CMK value. CMK value, you remember, that is the plant with the higher accuracy between the two. So, is it plant A or plant B that has the higher CMK and thus the higher accuracy between the two? Which is the one that is more on target, plant A or plant B? In this case, the answer is plant B. It's the other plant because plant B is on target. If you calculate the average value out of all the torque results that we have from plant B, that average value is exactly 7 Newton meters, the target. In case of plant A, instead, we have an average value of 6.8 Newton meters. That's not even in the accepted range for this type of application, so that must be a very, very bad CMK, so a very low CMK value. So far, we talked about CM and CMK as they were two separate things. Let's try and combine them together, and let's try and see what we can say about a tool depending on their CM and CMK values. We have a table here where we have 4 quadrants. These 4 quadrants will show us what happens when we have a high CM and a low CM value combined with a high CMK and a low CMK value. The first case is the one at the bottom right section of the screen, and that would be the high CM and the high CMK value. We know that high CM is good repeatability, high CMK is good accuracy. It means that the tool is good, the tool is perfect for the application that we have on the line where we want to use the tool. The other case that we have here already shown, the one to the bottom left of the table, would be a high CMK value and a low CM. The quadrant reads that that is impossible. That is impossible. If you think of that, having a low CM value means that my results are spread away one from the other, but at the same time those will be accurate. That's what the CMK, the high CMK value tells us. So that's impossible. It's really impossible to have these conditions happening at the same time. Let's go now to the upper left quadrant where we have a low CM and a low CMK value. Both the results are low ones. The tool is neither repeatable nor accurate. So that tool is not good for the application. And now the tricky question, I have to warn you, that is going to be a tricky one. What happens when we have a high CM value and a low CMK value? Is the tool a good one? Is the tool not a good one? What is the truth here? Think a little bit about it, and I'll tell you that the answer is that the tool is good in the end. Having a repeatability, having a high repeatability is really a characteristic of the tool. You cannot change the nature of a tool to make it more repeatable or not. If you have a tool that starts with a low repeatability, you can do whatever to the tool, but if it has been designed that way, you cannot change its nature. What you can change instead is whether the tool is hitting the target or not. So you can recalibrate it, you can adjust it. Sometimes it's only a matter of a setting to adjust a CMK value and to have a higher CMK value. Instead, the CM value, as I was telling you, that is really part of the nature of the tool itself. So, how do we use all of these for the initial tool verification? That is the first pillar that we have in our temple, in our best-in-class in quality temple. The way to do these inspections, as these inspections usually are done before you assign the tool to a specific joint on the production line, we do that in a tool crib environment or in a place where we are stocking the incoming tools. So we don't need anything that is mobile. We just need a bench, for example. That could be a good solution because you have all the transducers on the bench and you will just leave the bench in the crib, or you can use a data collector, and the data collector, you will probably use that with a static transducer. You just need transducers that will be fixed on a workbench rather than have a mobile type of transducer. So once we've done the initial tool verification, we're finally ready to assign this tool to a specific application on the line. And once we assign the tool to a specific application on the line, we have a different type of question. Our manufacturers will probably be asking themselves, is the joint being correctly tightened or not? So that would be a very important question. Think, for example, of the wheels of the joints that hold the wheels together on a vehicle. It's very important to be sure that those have been produced correctly and that the right amount of torque is there installed on those joints. So, how to do that? We need to do a joint inspection. The joint inspection is what is capable of reading the torque left in a joint after production has been completed. This is what happens during production. During production, what we have is that torque increases as we turn the joint around. So the more we turn the joint, the more torque we see. After this has been completed, we have some effects on the joints, like for example the relaxation. So torque could be changing. It would be not exactly the one we found, the one we installed with the dynamic torque. So what we do is a residual torque test. If we try and tighten again the same joint, we will see that at the beginning we have a very steep trace. That is because we have to continue applying torque until we are able to win the static friction on the joint. Once we're able to win the static friction on the joint will start moving and we will see the characteristic of the joint again. So the section from the residual point, that is where the joint starts moving, where we have won the static friction of the joint, up to the point where we stop applying torque, which would be the peak point. What are we interested in? We are interested in the residual point because that is the point that is telling us what was the torque which was left by production after the joint had been produced, after the joint had been tightened. This behavior is one of the typical behaviors, but in truth there is a second one. The second one occurs whenever you have a static friction which is higher than a dynamic one. I think we all experience static and dynamic friction when we ride a bike. In order to start a bike, we need to apply a lot of force with our foot on the pedal, but when the bike is moving, we need less and less force. The reason is that at the beginning we have to win the static friction that is present between the bike and the road, and in the second case, as we're going, we just need to keep on winning the dynamic friction that we have between the bike and the road again. So this happens with the joints as well. In case we have a high static friction to be won, that's when the bolt will start moving, and that point is called the breakaway point that you can see here on the graphic. Then you have a decrease in torque, in the torque that you read, because that is due to the fact that now we have a dynamic friction. This is what we're reading here. This is the residual point. So this is the torque that was left in the joint at the end of the production process. This is part of the routine residual online verification, and this is an inspection that can be performed by using a wrench. You could be using any type of wrench, but really the suggestion here is to use an electronic one, because if you don't use an electronic one, probably you're only reading the peak torque, which depends on the operator. If you use an electronic one, electronic wrenches have different types of programs that can be used, different types of strategies and algorithms that can be used to identify what is the residual torque point that we have on the joint. Now, as we keep track of our joints, there could be something that still goes wrong, because we might be having a not okay joint inspection. So what happens in case we have a not okay joint inspection? Whose fault is it? What do we do in this case? So we need to run an investigation, we need to find the root cause for the joint not being correctly tightened. If we look at what Six Sigma is telling us, a manufacturing process is influenced by 6 variables. These variables all start with an M here, and they try to force the M letter at the beginning of each of these ones, but these are quite easy to understand. They would be the method, the way you're running the process, Mother Nature, the environment. It would be very different to do a tightening in a plant with 50 degrees rather than in a plant that has a temperature of more than 100 degrees Fahrenheit. So that would change very much the type of manufacturing process that you would have. Man here really stands for person. Remember, I told you that they're forcing the letter M. That is the person that is doing the process itself. Measurement is the way you are doing the measurement, the way you are measuring, in our case, the torque that you have on the joint, the dynamic torque that you have on the joint. Machines, in our case, talking about a tightening process, would be the tightening tools and the materials. Think of a supplier that at one point switches the materials with which the joints are produced. You will have a different behavior in your tightening process. So, what is the first thing and the easiest thing you can look at in order to understand whose fault it is that you have a bad joint being tightened? The first possible culprit usually is the machine, is the tool itself. So that's something that we can easily inspect. We can easily see whether it is the tool that is not performing correctly, and that can be done by using a rotary transducer. So you just place the rotary transducer in between the application and the tool itself, and you can read the torque output from the tool by using a data collector. This is part of the reactive dynamic online verification. You see, this is a reactive process because we had a not okay tightening. If you're doing a lot of inspection, a lot of joint inspections, you can be sure that nothing is escaping your control. But if you don't do enough of them and you still want to have a proactive approach to checking the tool, probably this way, the reactive way, is not the best one, and it's better to put in place a routine dynamic online verification process to be sure that the tools are proactively performing accurately. So, how to do that? We have a different statistical tool. The CMC&K is not really suited for this type of application because CMC&K requires that you do 20-25 round downs, and when you have a tool on the production line, you really cannot afford to wait for 20-25 round downs to be done in order to assess whether the tool is working correctly or not. Luckily, we have this different statistical tool, which would be the SPC. SPC stands for Statistical Process Control. This is a method for checking the quality of any statistical process. In our case, it's the behavior of the tool. So by collecting a few samples every day or like at every shift, we can compile a chart which is called XR chart. The X chart is basically showing all the different points, all the different torque results from the tool as time goes by. So we can see the behavior in time of our tool. We can see whether our tool is trending or not. And let's say that you can see that the torque results from our tool are trending, and before they go out of specification, what we can do by using this tool is to proactively readjust the tool before it goes out of specification. So the best way to do it, really, to run the routine dynamic online verification would be to use a joint simulation bench. I'm specifying joint simulation bench for one reason, because you can, as the bench is mobile, you can place it next to the station where the tool is located, and you can run an SPC inspection by doing 3 to 5 round downs very quickly without interfering with the production line, because a joint simulation bench would be very fast to be used, and at the same time it is simulating the joint that you have on the production line. So you're not interfering with production and the joints being produced, but you are simulating exactly the same operating conditions for the tool using a joint simulation bench. So I think that these will really cover every single aspect, the whole lifetime of a tool, if we think from the moment it's delivered to the plant up to its entire life during the manufacturing process. Is this enough? We still have, remember, 2 pillars to go, and there is a specific reason. If you look at this picture, you will see that there are a lot of transducers in this picture. Some transducers are the ones that are on the tools themselves, and any tool manufacturer will tell you that the tool transducers need to be periodically calibrated. A suggestion usually is to do that once a year. That's a typical suggestion, but that can change depending on how often the tool is used, how much that is used, which type of application is being used. That can change the amount of time between which you do 2 different calibrations. So in order to do this, in order to calibrate a tool and to do a routine tool transducer calibration, what you need to do is to read the reading from the transducer and compare it against something that is more accurate. We usually say 4 times more accurate, and a solution in this case would be joint simulation benches, rotary transducers, and data collectors. With these tools, you can compare the readings and you can evaluate a new calibration value for your tool so that you can readjust the tool and be sure that it's working as accurately as it's meant to be working. On the other hand, remember we had some other transducers in the picture that I was showing you, and those are all the transducers that we have in our plant standards. The plant standards being all the transducers that you need for quality assurance. These transducers are already more accurate than the transducers that you have on the tool, and those need to be maintained to the correct level of accuracy, and they also need to be calibrated in order to do that. Of course, you cannot calibrate them with the same types of transducers. You need transducers which would be more accurate. For this reason, this type of calibrations are usually performed by a calibration lab, and the calibration should be certified with an ISO 17025 certification. So this is needed to ensure that your plant standards are still working correctly. We covered with this one the routine plant standard calibration. This would really be the last of our process here. There is one other process that's not really explicitly named in the pillars in our temple, because this is something that is related to everything really. It's related to the prerequisites as well, and that would be the data retention. Think of all the data that you're collecting with the different types of inspections, with the different processes that you have to become the best in class in quality. And all of these data need to be stored, maintained, and need to be accessed, because of course you might be having audits, you might be having the need to review what was the situation in a certain period of time. So that's why it's very important to have the right software that is capable of collecting all of these data and to have them accessible for future reference. All the processes that we have in our pillars, we need to specify a few things, and those will be the prerequisites. We need to specify torque. We need to have the torque specifications for the dynamic torque and for the residual torque. These could be different one from the other because of effects like the relaxation that I was mentioning earlier. We need to classify the joints. Not all joints are born equal, so we have some joints which would be safety joints, like the joints that you have on a wheel. Those will have a different level of accuracy, a different level of performance they require as compared to a joint that is needed only for a loudspeaker in a vehicle. We need to maintain all the processes, documentation updated so that the whole plant can reference those processes by using these documents. We have to retain the data, as I was already mentioning earlier. We need to have data accessible and have all the equipment correctly calibrated. This is really part of one of the pillars that I was talking about earlier, but being sure that everything is traced back to the industry standards ISO 17025. If you put all of this together, I know it's a lot of processes. You can start from any of these processes. Besides the terminology and the prerequisites, when you want to become better at the quality that you have on your manufactured goods, each of the pillars will be a good starting point. So you can start from any of those points, and then any point will help you improve the quality in general. Once you achieve all of the 6, you can be sure that you became the best in class in quality.